In this video, we continue the presentation of the package xTensor, which is part of the exact package for Mathematica, for doing tensor computations in general relativity. And not only, but we confine ourselves to the case of general relativity. You need the package xTensor, which is included in exact, and in the previous video you will find instructions on how to install it in your system. Watch the previous video or visit the exact page for more detailed instructions on how to do that. First, we have to load the package with the function needs. And then we define a manifold. In our case, it will be a four-dimensional manifold. That is the second argument in the function def manifold. We use the symbol M4 for the manifold, and this is the list of indices that can be used for the tangent bundle of that manifold. This will be a manifold with a metric for which we use the symbol G. It has two downstairs indices, mu and nu, which must be in the list of the previous call. And it has a Levi-Civita compatible with the metric and torsion-free covariant derivative, which we use the symbol CD for it. There is a lot of information here, and as we have already stressed in the previous video, it contains lots of useful information for all the symbols that have been defined that correspond to the tensors that are related to this metric, like RiemannToChristoffel, Ricci tensor, EinsteinToRicci, Christoffel symbols, etc., etc., etc. Then, in order to practice, we will define a set of tensors. We use the function def_tensor. Def_tensor here takes two arguments in its simplest usage. The first one is the symbol we use for the tensor. For example, in this case, it is a vector u. Then the indices, and that is what defines the rank of the tensor. Lower indices and upper indices are different. Then the manifold that corresponds to the tangent bundle that those vector fields will belong to. And when the tensors have symmetries for some or all of their indices, we can specify them with the functions antisymmetric and symmetric. So after this call, all those tensors, the vectors u, v, w, the one forms xi and omega, and the 2, 0 and 0, 2 tensors f and s have been defined and can be used in expressions. F is antisymmetric and s is symmetric. Riemann CD is the Riemann tensor that corresponds to the affine connection CD. So we write it in this form. In the conventions that are used in xTensor, this is defined with three lower indices, mu, nu, lambda, and one upstairs index, sigma here. And that can be more explicitly seen in the output form of this object here. So you see it has the symbol r, then the covariant derivative that is used for this Riemann tensor is put here in the square brackets, and the indices are placed in the right place. So we can use Riemann CD to write down expressions that involve the curvature tensor. So for example, we can contract those indices with those coming from the vector v, u, w, and the one form omega, and that will give us this result in this form. Now, as we know, the Riemann tensor has some symmetries. Some of those symmetries are monoterm symmetries. And by monoterm, we mean that they just have one term. So, for example, the Riemann tensor here is antisymmetric with respect to the exchange of the first two indices. That is a monoterm index because symmetry, because r mu nu is minus r nu mu. But there are also multi-term symmetries, like the one that says that the antisymmetric part with respect to the three antisymmetrization of the first three indices, mu, nu, and lambda, is equal to 0, that has more than one terms. So monoterm symmetries are built in xTensor. So if I put here, instead of u, I put v, this expression should be equal to 0. Why? Because it is antisymmetric with respect to the exchange of the first two indices, mu and nu, but it is symmetric with respect to the exchanges of the indices mu and nu here. Now, if I evaluate this expression, that will not be equal to 0. In order to apply the symmetries, I have to use the function to canonical. And then you see that this expression is simplified to 0. So let's look at the multi-term symmetry of the Riemann tensor. So we know that this should be 0, but it is not. So let's call this equation 1. Now, the best we can do is to write this in a canonical form. But still, we will not be able to sorry, there is a mistake here. I have to apply to canonical. So you see the terms are reordered as well as their indices, but we still don't obtain a result that is equal to 0. And the same is true if we try to apply simplification. So for that, there's a whole chapter devoted in the documentation of xTensor, and there it is explained how to use more complicated symmetries of the Riemann tensors in your expressions. So read section 9.2 of the notebook xTensor doc.nb included in the documentation of xTensor. So let's look how we can write down this expression that should be 0 because of the symmetries of the Riemann tensor. We can use the function antisymmetrize, and we obtain the same result as before if we apply simplification. So multiplying this by 3 will give us the same expression as before. Now, the contravariant Riemann tensor is obtained by lowering the last index using the metric. This is possible only if there is a metric in the manifold which is used for lowering the index. And we know that this tensor has more symmetries than the Riemann tensor with the index upstairs. So, for example, here we obtain this expression here. And that will give us this result here. So now let's anti-symmetrize only with respect to the first two indices. So we know that because of the antisymmetry property of the Riemann tensor, this should be equal to the Riemann tensor itself, and the same thing is true as we have already done with the Riemann tensor if we antisymmetrize with respect to the first two indices. Now, if we symmetrize, we obtain this expression, but this should be 0. In order to apply the symmetry properties and obtain 0, we have to act with the function 2 canonical. And the same result will be obtained if we antisymmetrize with respect to the last two indices. Again, this is equal to 0. Now, another property that the Riemann tensor with all the indices downstairs has is that it is symmetric with respect to the exchange of the pairs of indices, min, e, and rho sigma. So here I'm writing an expression that should be equal to 0. Now, this symmetry is built in xTensor, and when we act with 2 canonical, we obtain 0 indeed. So let's play a little bit more with the symmetries of the Riemann tensor. Now, here you see that we act with the same, we contract with the same vector, w, lambda, and w sigma, the last two indices of the Riemann tensor. This should be equal to 0, and we see that when we apply to canonical. Now, this expression should also be 0 because we use the metric, which is symmetric, to lower the second index here, so to raise the second index here. Now, this will be shown to be 0 when we apply the monotone symmetries of the Riemann tensor, and indeed, 2 canonical does exactly this. Similarly, we can contract the last two indices of the Riemann tensor. That should also be equal to 0. And we see that when we apply with the function 2 canonical. Now, let's write down this expression here. Now, this expression is the Riemann tensor contracted with the Ricci tensor in the first two slots here, mu and u. We know that the Ricci tensor is symmetric This is anti-symmetric, therefore this has to be equal to 0. And indeed it is. Another expression that should be 0, we contract now with the Einstein tensor. The Einstein tensor is also symmetric in its two indices, and now we contract with the last two indices of the Riemann tensor. We apply two canonical, and that will also give us 0. Now let's write a more complicated expression. So you see here that we contract the indices nu and sigma, the second and fourth indices of the Riemann tensor, with the Ricci tensor. And then we contract the indices nu and lambda with the Levi-Civita tensor. Now we obtain this expression. You see that this expression is equal to 0. Now, why is it equal to 0? Well, you can take some paper and a pencil and show that indeed this is equal to 0. Now, let's examine the tensors that are obtained using contractions of the Riemann tensor. The first tensor that we know is the Ricci tensor. There's a special symbol for it. It's called Ricci. You remember the convention of xTensor. It takes the name of the tensor and appends the name of the covariant derivative that it corresponds to. And you see that the output form of the Ricci tensor is similar to the one for the Riemann tensor, but it only has two indices. Now, you know that the Ricci tensor comes from contracting the second and fourth index of the Riemann tensor in the conventions used in xTensor, of course. And you see that when you contract those two indices, this is replaced by the Ricci tensor immediately. Ricci scalar is the Ricci scalar that corresponds to the covariant derivative CD. And its output form is given by R and then the symbol that is used for the covariant derivative. You know that the Ricci scalar is obtained by contracting the two indices of the Ricci tensor, and that is immediately done when we write down this expression here. Now, the Einstein tensor has an output form given by the letter G here. Now this is the covariant derivative it corresponds to. Now you know that the Einstein tensor is given by this expression here. Now there are functions that convert between Einstein tensor and the Ricci tensor, which are called Ricci to Einstein and Einstein to Ricci. So if you write this expression here, you will obtain the output form of the Einstein tensor, But if you apply the function EinsteinToRicci on it, then all the Einstein tensors in this expression, which of course it is a very simple one here, will be replaced by their equal, which you see it corresponds to that expression here. Now the opposite can be achieved by using the function Ricci to Einstein. So that is an expression that has the Ricci tensor in it. We can apply the function Ricci to Einstein on it, and you see that the Ricci tensor has been replaced by the Einstein tensor. Now those two terms here still remain. Of course they're equal to 0, but in order to see this, we have to apply the function to canonical. And indeed, we find the same result. Another tensor that is useful in general relativity contains all the propagating degrees of freedom in 4 dimensions is the Weyl tensor. So there is a special symbol for this, and if we have expressions involving the Weyl tensor, we can convert all the instances of the Weyl tensor to the Riemann tensor by applying the function Weyl to Riemann. So this is a way, if you have forgotten how to express the Weyl tensor in terms of the Riemann tensor. So there is this Riemann tensor here, and then there are the terms involving the Ricci tensor and the scalar curvature that remove all the dependence of the Riemann tensor on those particular contractions. Another tensor that might turn out to be useful in some cases is the trace-free Ricci tensor. The symbol used for it is TFRicci. So trace-free Ricci, that is where the name comes from. Its output form is given by S here. And indeed, this term here, this tensor here, is trace-free. So if you contract its 2 indices, the result will be equal to 0 by definition. Now, if you want to see how you can express this in terms of the normal Ricci tensor, there is a special function called TFRicciToRicci. And you see this expression here, which depends on the number of dimensions. We can also take expressions that involve the Riemann tensor, like this one, and write them in terms of the Christoffel symbols, of the covariant derivative or the affine connection that the Riemann tensor comes from. The function to do this is called RiemannToChristoffel. So we obtain this expression here. It has those ugly dollar indices here, and as we have shown in the previous video, we can make them go away by using the function screen dollar indices. And here you can see that what is the convention used for the Riemann tensor, and compare it to the one that you use. For example, in our class, we use the convention of the Riemann tensor defined in Carroll's and Hartle's book. And xTensor uses the convention used in Weyll's book. So there is a difference in the sign and in the placement of the indices. So here you see mi and ni are placed in the beginning, and mi and ni are placed in the end in Carl's book. And then the indices that rotate the vector or the one form in the commutator of covariant derivatives definition are the first two indices in Hartl's book and the last two indices in the other order in Weyll's book. So we can write the expression involving the Christoffel symbols also for the Ricci tensor, and for that we have to apply RiemannToChristoffel and show this equation here. The Ricci scalar can also be seen in terms of the Christoffel symbols. It is a scalar, that's why you see those red parentheses here that separate this expression as a scalar. That is a feature of xTensor which is more advanced. Read that in the documentation. Now, if you want to see a similar expression for the Einstein tensor, first you have to obtain an expression that involves the Riemann tensor, like the Ricci tensor, and on it you can apply the functions RiemannToChristoffel to have an expression involving the Christoffel symbols. So you can do the same thing for the Weyl tensor. The Weyl tensor has first to be transformed to an expression involving the Riemann tensor, and that expression can be transformed to an expression involving the Christoffel symbols. So RiemannToChristoffel can be used as a first step to obtain expressions that involve only the metric. So here is a very simple expression, of course, with just one term. First, we transform it to an expression that has the Christoffel symbols, as before. Then we can apply the function Christoffel to grad metric, which we have discussed in the previous video, that converts the Christoffel symbols to expressions involving the metric and its derivatives. So, if this expression is useful for you, you can use it in your calculations. So, we had defined the Riemann tensor in terms of the commutator of the covariant derivatives. So, let me remind you the definition here. So, this is the definition used in xTensor. It is the same as the one used in Weyll's book. So the commutator of the covariant derivatives of V is minus R, with the indices placed this way, and on one form it is with a plus. And in Carl's definition, We have the new indices here put last, and the ones that rotate or transform the sigma index here to rho placed in the beginning. And there is a plus sign here. So you see that you can compute in this way the correspondence between the two tensors. So the Riemann tensor has a minus sign with this placement of the indices, but notice that if you consider the Riemann tensor with all the indices downstairs, then the two definitions coincide by the symmetries, using the symmetries of the Riemann tensor. So in the previous video we had shown how to compute the covariant derivative of a tensor. So here it is the derivative of a vector v, and then if you want to differentiate again, you can apply the derivative here in the beginning, and we had explained why you can use the map_at symbol of Mathematica to write down the expressions in this form. So this gives us the second derivative of the vector v, and the commutator can be computed by subtracting the derivatives taken in the opposite order. So that is the commutator d nu acting on v. So let's manipulate this expression and obtain expressions that have the Riemann tensor as defined in those relations shown before. So there is a function which is called sort covariant derivatives, SortCovDs. So that will take all terms and put the covariant derivatives in a canonical order. So we obtain again this expression involving dollar indices, which we can screen with the function screen dollar indices. So you see here that we have obtained the definition shown above. Okay, of course here we have a plus sign, but you see that the first two indices are nu instead of nu, so that gets rid of the minus sign. Similarly, we can compute the action of the commutator on the one form here, and again obtain an expression that gets rid of the commutator and replaces the equivalent expression involving the Riemann tensor. This way, you can see the action of the commutator on higher rank tensors. Which now involve two terms, one for each index of the tensor FAB. Now another function that can be used in expressions is the one that commutes the derivatives on a particular term. So let's take this action of two derivatives on the vector v. Then there is the function which is called CommuteCovDs that takes an expression in its first argument. Then we have to explain to it which covariant derivatives we want to commute. Remember that xTensor works in environments where multiple covariant derivatives and multiple metrics can be defined. So here we specify that it is the covariant derivatives of CD that we want to compute. And then, in the end, we will have to say how we want the indices to be ordered. So here you see the indices are written here in the new order, and here we say that we want them to be written in the terms of new order. The result of this will involve again the dollar indices, so we apply the function screen dollar indices to see something nicer. So you see that d nu of v is replaced by d nu v plus the term that involves the Riemann tensor. Now, some other properties that are built in xTensor that are important is, for example, the fact that the divergence of the Einstein tensor with respect to one of its indices is equal to 0. So for that, you don't need to apply to canonical, it is built in. And as we have already seen, when we contract the correct indices in the Riemann tensor, we obtain the Ricci tensor. The Weyl tensor has this symmetry here, that when we contract those indices here, we obtain 0, and that is something obvious because we have defined the Weyl tensor so that to be the Riemann tensor with all the dependence on the Ricci tensor and scalar curvature to go away. And the other property here, that is by definition the trace-free Ricci tensor has a trace that is automatically equal to 0. Okay, so let's play a little bit with what we have learned and prove the Bianchi identities for the Ricci tensor. So you can find this in this notebook, which is posted in the exact documentation page. So first, we write down the antisymmetrization of the Riemann tensor with respect to its first three indices. And we know that the first Bianchi identity tells us that this expression should be equal to 0. But as we have seen above, even by applying simplification, this is not built in xTensor. So let's multiply here by 6 to get rid of the normalization factor and call this expression equation 1. So that is equation 1. So the first thing that we will do is to apply RiemannToChristoffel and screen the dollar indices. And we obtain this expression here. Then we convert this expression to an expression that involves the metric. That is a seemingly complicated expression, but if we canonize it, then this is equal to 0. So this is how we have been able to apply this symmetry in this expression here. Now let's consider the second Bianchi identity. The second Bianchi identity takes the covariant derivative of the Riemann tensor and antisymmetrizes with respect to the first three indices of the expression, one involving the derivative and the first two ones from the Riemann tensor. So again, we multiply by 6, call this equation 1. So again, equation 1 we transform it to an expression that involves the Christoffel symbols here. And then you see that the Christoffel symbols here are covariantly are acted by a covariant derivative here. So we can get rid of this covariant derivative by converting all covariant derivatives to Christoffel symbols. And we obtain this expression here. Again, this is a seemingly complicated expression, but xTensor can transform it to 0. So let's go to another chapter now, which involves on how to manipulate our expressions, because in the end this is where the heart of our computations lie, and discuss how one can use assignments and substitution rules in tensorial expressions. As we have already said in the previous video, tensors are objects that are complicated in xTensor, and many times it's not very wise to use the assignment and rule functions that Mathematica uses for its more simple expressions. So there are special functions that do this job, and first we will start with the functions IndexSet and IndexSet delayed, and this is equivalent to the equal sign in different expressions. So instead of saying A equals B, we will say IndexSet A comma B, but the result will be that the symbol A will now be substituted with B everywhere in all expressions. The functions IndexRule are the ones that are the same as substitution rules in Mathematica, and they are used for temporary substitution of tensorial expressions in our equations. So first, let's define some temporary tensors to play with. So we define the tensors TMP1, TMP2, and TMP3. TMP1 is one form as well as TMP3. And you see that although their input symbols are complicated, their output form will be simple because we use the print as option here, and they will be printed with a single symbol, T, T capital, and Q. So if you write now TMP1, you see that we obtained simply T mu because it is printed this way, and 3 is printed out as Q mu. U02 is printed using the capital T letter, capital T character. So let's now use the function IndexSet this way. So let's dissect this expression. So IndexSet here takes two arguments. The first one is the tensor TTMP1. TTMP1 takes a downstairs index minus mu, and we put here the underscore to mean that this is an expression with anything. Now the second argument is what TTMP1 will be substituted for, and you see that it is the contraction of the tensor f, which we have defined in the beginning of the notebook, and the vector v. So after the call of this function here, whenever we write TTMP1, it will be substituted by the second argument here. So when we now write TTMP1 minus mu, you see that we obtain the expression involved in the second argument. Let's screen the dollar indices to have something more nicely looking. So you see that instead of T mu, we obtain the tensor that we used in this assignment function. And if we change the index will be also changed. So the fact that we used the underscore here means that we can use any index that we want there. So in Mathematica, these are called patterns, and any pattern there involving this index will be substituted with the assignment tensor here. So let's write a more complicated expression. Again, let's screen the indices. So you see that each instance of the tensor TTMP has been replaced by FV. We can simplify this expression by contracting the metric with the function contract metric. We have seen this function in the previous video, and all the contractions with the metric are performed, and we obtain this final expression here. Now look at this expression here. So we have contracted TTMP1 with its two indices, and you see that although the downstairs index has been replaced by FV, the expression involving the index upstairs is not. So let's cure this by making a double assignment. So TTMP with minus mu is replaced by this, and TTMP with index upstairs is replaced by this. Then this expression here is now replaced by its equal, which is the same as the one shown here. Now let's look at the function IndexSet delay. So IndexSet delay corresponds to the Mathematica assignment A column equal B, and this is a delayed assignment in the sense that when we write A, it is substituted by the value of the right-hand side that occurs at the particular time that we make the substitution. Whereas if we make a direct assignment like this, then A is replaced by whatever value B has at the time of the assignment. So similarly, IndexSet is corresponding to a direct assignment like this one, and IndexSet delayed corresponds to an assignment like this one. So here, TTMP2 will be replaced by F times TTMP3. But now, the assignment will be evaluated at the time when we use TTMP2 in our expression. So let's look at it, how it works. So you see now that we obtain, in place of TTMP2, we obtain F times Q. Okay, you remember that TTMP3 is printed as Q in our definition here. We have printed as Q. So let's now write a rule for TTMP3. So TTMP3 is replaced by S times V. Sorry, S contracted with V. Okay, so let's now compute this expression here. So you see that instead of obtaining F times Q, we now obtain the value that TTMP3 has. If this had been a direct assignment, this would have been a different result. And then we can reassign TTMP3 to be Ricci contracted with V, and when we write down this expression now, you will see that instead of S times V, we have the new value of TTMP3, R times V. Now, let's use rules. What are rules? Rules are expressions that make substitutions but without making permanent assignments. So, if we take, for example, the vector v, then we can use IndexRule to transform it. So IndexRule works something like v goes to g times omega. So now you see that this v has been replaced by the expression found here in the second argument of IndexRule, and the value of v has not changed, so it is the same as before. Now, this is another example. This is the one form, omega. And this is an expression where omega has been substituted by the vector v with its index lowered by the metric. So by applying contract metric, we can have, in place of the one form omega, the one form v. Now, because substitutions are very important, there is a symbol that has been introduced by xTensor for it, which, if you like, you can use. It is similar to the one used by Mathematica. In Mathematica, you just press escape dash greater than escape, and you have this arrow here that has regular substitutions. Now, the symbol here is an arrow with this little line here in the beginning called right T arrow, and you can type it this way: backslash square bracket right T arrow. You can now press the tab for an auto-completion, and there it is. So now I can write that rule here the same way that I write rules in ordinary Mathematica expressions, and I want omega to be substituted by g and I obtain the same result by applying those two functions. Now, sometimes we want to make substitutions or apply functions not at the full expression, but at parts of it. Now, if you want to do that, there is an optional package in Mathematica, in Exact, called expression manipulation, which you have to load. Now, let's write a tensorial expression here. We call it equation 1. So that is equation 1. And now expression manipulation gives us several options to work with that expression. One of it is to see the different terms in colors. So you see that expression manipulation considers this expression as an expression of three terms. That is the first term here, the second term there, and the third term there. So let's do something more useful. So that is equation 1. And one possible thing that we might want to do is to apply RiemannToChristoffel. But you see that RiemannToChristoffel is applied to all of those terms. Suppose that we want to apply RiemannToChristoffel only to the first term, the second term, or the third term. what could we do? So this expression manipulation package here allows us to apply, in this case, Riemann-Tochristoffel only, let's say, at the first term. And for that, we have to use the function map_at. So map_at here takes two arguments. The first argument is the function that we want to apply to our expression, which in this case is Riemann-Tochristoffel. The second term is the expression. In our case, we have named it to the symbol equation 1. And the last term here says that I want this function to be applied only on the first term. So you see here that only the expression involving the f-tensor here has the Ricci tensor being substituted by the Christoffel symbols. And the one here, the second term, is not. Now if I want this to be applied to the second term, then the first term is left intact, and the second term is transformed to an expression involving the Christoffel symbols. Now you can apply the function to more than one terms by using this syntax here. So using this syntax, we can apply this function to both terms 1 and 2, but not 3. And we obtain this expression here. Now, we can use functions in this package also to find the pattern in an expression. Let me show you an example here. So this is our tensorial equation here, expression here. And let's say we want to find terms that contain the Riemann tensor. So we use the function color positions of pattern, and then the pattern is whatever that has the head Riemann CD. And the head Riemann CD is found only in the term that involves the Riemann tensor here. Now the other terms have the Ricci tensor, there's no Riemann CD head here, and the Weyl tensor, also there is no Riemann CD there. So here you see that only the term 2, 1 is the one that has this particular pattern, this particular head. And then we can use this expression here to apply this function, Riemann-Tochristoffel, to our expression only at the position where you find a Riemann tensor. So you know that Riemann-Tochristoffel can also be applied on terms that have the Ricci tensor, which also can be found in term 1. So this way we say that we want to make the substitution only in the parts of the expression that involved the Riemann tensor. And you see that this term here is left intact without making the substitution. Rules and the substitutions made by them are very important things. A more powerful function to construct rules is called MakeRule. So we have seen the function here, IndexRule, but now I will show you how to use the function MakeRule. So MakeRule makes rules, but without using patterns in the definitions. So this is an example here. So the rule here, you see it has one argument only, and it has list. A list can have more than one rules, as we can see later. So this rule here takes your expression and substitutes omega mu by the Ricci tensor contracted with the vector u. After you have this rule defined, you can take an expression like this one and apply this rule using the usual syntax of Mathematica. So you see that omega mu has been substituted with r times u, r contracted with u. Let's make more complicated rules. Now, this is a rule that substitutes the one form omega by the covariant derivative of f contracted with rho and nu contracted with the index of the covariant derivative. Now here we see some options that can be turned on and off. I think these are the default options, so this is just for displaying the possibility of using those options or not using them if you want. So we can now write this expression here and apply rule number 2 to it. So you see that u, the u vector here, remains as it is, but omega has been substituted with the covariant derivative. The covariant derivative involves the product of those three tensors. So the Leibniz rule is applied and we obtain three terms in its place. So let's simplify this. And that is the final result. Now, let's try to make a more composite rule. In this case, let's say that we have an expression and we know that the covariant derivative of u is equal to 0. And we want to substitute that to our equations. So we define a rule that says that the covariant derivative of u is equal to 0. That is rule 3. So again, let's write this expression here. Let's apply rule number 2 to obtain this. So here you see that we have two terms that involve the derivative of u, and we can get rid of them by applying rule 3. So this is the final result. Now you see that this expression is antisymmetric with respect to the exchange of indices mu and beta because of the symmetry properties of F, but symmetric with respect to the exchange in this UU term. So this result should be equal to 0. And we can see that by applying simplification. Okay, so now let's use MakeRule to do a more realistic computation. Let's compute the equation of geodesic deviation. So let me remind you a few things. First of all, we have this congruence of geodesics. V is the tangent vector, so V dV must be equal to 0. And then the relative position vector U is such that it defines a coordinate system, therefore it commutes with V. And the commutator being 0 means that V du is equal to U dV. Similarly, the other way, U dV is V du. If you remember the proof, which of course you will find that it is easier to do it on paper than in the computer, but remember we're just practicing now, involves applying the Leibniz rule and also some contraction. So you will see that these have to be made explicitly as ordinary rules of these rules must be defined explicitly with the function MakeRule in order to be applied to our expressions. So we will give names to those rules. You see them here in the first column. So that is the rule V geod. So that replaces V dV by 0. That is the first equation here. That is this replacement. Now the rule that involves the commutator of V and U replaces V du by U dV. Then the third rule that replaces U dV by V du. So you see, this is U dV and this is V du. And then the Leibniz rules, slightly more complicated here. So we want to replace V ddV by the d of V dV minus dV dV. So that is the left hand side of the rule, and that is the right hand side of the rule. And then the last rule here that replaces V ddV by this expression here. So let's start by writing down the acceleration. So that is V d of V du. So we see the Leibniz rule is applied. Now let's substitute v du by u dv. So I will take this expression here, and instead of it I will differentiate u dv. And then I can also expand it using the well-known Mathematica function here. So I like this expression, so I keep it in a symbol TMP1. That is TMP1. So now I want to replace v du by u dv. So I take this expression and apply the rule vu to uv. So you see that v du has been replaced by u dv. So I like this. That is my expression TMP2. And now if you remember the analytic proof, I have to commute the derivatives here, d rho d alpha. So I will use this expression here and commute those derivatives by applying the function CommuteCovDs that I showed you earlier. So I want this rho alpha to be commuted to alpha rho. So that will give me this expression here. Let me also expand it. And then I obtain this expression here. So let me call this TMP3. Now, if you remember the proof that I have shown you analytically in a previous video, it involves applying the first Leibniz rule to this expression. Then you see this v d dv has been replaced by that. So this is where v d dv lies, and it has been replaced by its equal here. And then by applying to canonical, I obtain this. And that is the geodesic deviation equation that tells us that this acceleration here is proportional to the Riemann tensor. So let's do another exercise. This is another exercise that I have shown you how to compute in a previous video. It states that for a Killing vector, this equation holds that d nu on xi is r times xi. Now, for that, you remember in this proof that we have to use multi-term symmetry properties of the Riemann tensor. And let's see how to work with that. So the first is to define a rule that applies the Killing equation. So the Killing equation tells us that d nu xi nu plus d nu xi mu is equal to 0. So this rule here replaces d mu xi nu by minus d nu xi mu. So we start by this expression here. That is the left-hand side of our equation. Let me call this as TMP0. And you remember in the analytic proof, we wrote many terms that involve the derivatives commuted in different ways. So here I have to go step by step and obtain all those terms. So we'll start commuting the derivatives and using the Killing equation at the same time. So let's take this expression here and commute the derivatives d mu to d nu d mu. So this function will give me the derivatives in the orders that I have asked, plus the Riemann tensor correction term. So let me call this TMP1. So I want to apply now the Killing equation. So that is TMP1, and I apply our kill to it. So you see that d nu d mu has been replaced by d nu d lambda and have the minus sign here. Now the indices also yes. So the indices mu lambda have changed order to lambda mu and have the minus sign here. So I call this expression TMP2. And again, I take TMP2 and I apply and I commute the derivatives here. From nu lambda to lambda nu. So the derivatives are commuted and a second Riemann tensor term has appeared. So that is my TMP3 variable. Now I apply the Killing equation and nu will change order. The minus sign has become plus and nu mu is now mu. So that is TMP4. And again, I am commuting the derivatives d lambda d mu to d mu d lambda. And that will be my variable TMP5. Now a third Riemann tensor term has appeared. And I apply the Killing equation to change lambda nu here to nu lambda. And I obtain this minus sign. So let's write this in a canonical form. So I have those three Riemann tensor terms. And now I will use an ordinary substitution in Mathematica and I will replace R lambda alpha mini by R mini lambda alpha. So that will exchange the pairs of indices of the first Riemann tensor here. So here is the term here, mini lambda alpha. And then I will apply the first Bianchi identity by hand by making this substitution here. So I'm taking R lambda mini alpha and replace it by minus R ni lambda mi alpha minus R mini lambda alpha. And then I will expand. And then to canonical. And you see that the equation has been proven. Why? Because the left-hand side is the left-hand side of this equation. The right-hand side is 2r minus ddxc, but you see the ddxc terms are the same. They can be brought to the left-hand side. So this is equivalent to the identity that we started to prove.